Okay, now let's look at inventory models. So before we get into inventory models, we need to understand the concept called independent demand and dependent demand. And these independent demand and dependent demand are about production decisions that we make for inventories. If demand for an item is independent of the production decisions we make, then those items are called independent demand items. For example, if we decide to produce model A of 100 units this week, that does not necessarily mean that the customer demand will be 100 units that day or that week. It could be less or more. So the demand for the finished products, the demand for items that we sell to our customers will make that decision whether to buy or not to buy, and that is completely independent of the production decisions we make. On the other hand, to produce a given item, for example, to produce this pen, okay, and the plastic that we need, the clip and the ink that goes into it. So if we decide to produce 100 units of this pen today, then we need 100 units of this clip, 100 units of this lid, and 100 units of whatever ink that goes into it. On the other hand, if we decide to produce 50 units of this pen today, then only we need 50 times these items. Or if we decide to produce none of this, then we don't need any of this. So the demand for all these items, the individual components that go into the final product, the demand for those items are completely dependent upon the decisions we make in terms of how much to produce and when to produce. So these items are dependent demand items, dependent upon the production decisions we make. So typically speaking, the finished product, the completed pen that we sell to our customer, so that would be an independent demand item, because just because we produce 100 units of this pen today, we may or may not have 100 or maybe more or maybe less or not at all of the demand coming from the customers. Whereas if we decide to produce 100 units of this pen, then the components needed for the production of this pen will definitely be needed. So these are dependent demand items. So dependent demand items, since its demand can be exactly calculated, the model, the inventory model that we will use is called material requirements planning, and that is the topic of chapter 14. Whereas independent demand items, okay, they follow different set of rules, because what the exact demand will be, we don't know. There are some fluctuations and so on. We cannot exactly calculate what that demand will be. Those are independent demand items. So we have models like EOQ and POQ and reorder point methods and so on. And those are the topics that we will consider in this chapter, in chapter 12. So independent demand items and dependent demand items. And the topic of this chapter is independent demand items. Dependent demand items will be discussed in chapter 14. Now let's look at the costs involved in developing inventory models. There are actually 4 different costs that you can think of. One is holding cost. The holding cost relates to the cost involved in keeping inventory in stock. The second cost is the cost of ordering or placing orders, and a corresponding cost in manufacturing environment would be setup cost. So ordering cost and setup cost are kind of related. Ordering cost is when you place an order with your vendor, so preparing the bids, evaluating the bids, placing the contract, and the costs related to receiving the inventory, those kind of costs that are specific to the administrative costs of placing an order. And a similar cost in a production setup would be setting up the machine, placing the tools, and calibrating the machines, the labor involved in setting the machine up to produce a batch of quantity. So ordering costs and setup costs are related costs. And there are 2 other costs that are important, but they don't play role in inventory quantity models as such, and those are stock out cost, and the stock out cost is a relevant cost only when we are looking at reorder point. So we'll be discussing stock out cost later on. And the other cost is item cost, and the item cost is not relevant at this point because on an annual basis the quantity that we have to order is going to remain the same. So the cost of the item is not relevant unless there is quantity discounts involved. When quantity discounts are available, then the order quantity and the cost of the item are related. So if there is no quantity discount, then cost of the item is irrelevant. So at this point we look at these two costs, holding cost and then ordering / setup cost, because ordering cost and setup cost are related costs. Now what is involved in holding cost? When you have inventory to keep in stock, so you have to have a warehouse and you have to have labor to maintain the warehouse, taking inventory into stock or taking inventory out of stock when needed, the material handling cost, and then the cost of capital locked in the inventory, and that will be a very large part. Cost of capital will be more than half of the holding cost will be towards the capital cost. And then there is also taxes involved, insurance, pilferage, and obsolescence. Obsolescence means, especially in technology related products, and if you keep too much inventory, before you could use the inventory, the technology changes and the inventory that you're holding becomes useless. It becomes obsolete. So in total, when you combine all of this, the holding cost can be as much as 20 to 25 to 30, even up to 40% of the cost of the items. The holding cost is really a huge cost. Okay, so 15 all the way up to 40%. Now let's look at modeling for independent demand items, and there are three EOQ models we will be discussing. The basic EOQ model. When we discuss basic EOQ model, we will be looking at several assumptions. So when we relax one or two of these assumptions, then we get the production order quantity model and the quantity discount model. So what are the basic assumptions? Okay, the demand is known and constant and independent. So that means if the demand is 10 units a day, it's 10 units every day. If it is 10 units a week, it's 10 units every week. So it doesn't fluctuate, it remains constant and deterministic. One may find this to be kind of a not very reasonable assumption to make, but it turns out that even if this assumption is not true, the EOQ model would still be a very robust model. We'll look at robustness a little later. And besides, if this assumption is not true, the EOQ is not affected. It is the reorder point that is affected, and we'll be discussing how to handle that situation. Like assumption number 1 is not true, then how do you mitigate that? And we'll be looking at that later on. The same case with assumption number 2. Lead time is known and constant. If the lead time is 2 weeks, it is 2 weeks every time. It doesn't change. It remains the same. This assumption is probably true in many cases, but if it is not true, once again, the EOQ formula is not affected. It is the ROP, the reorder point formula, that will be affected, and we will look at that later on. Now, the third assumption is receipt of inventory is instantaneous and complete. So that means the entire quantity, order quantity, is delivered in one single lot in one instant in time. If this assumption is not true, then the delivery of the batch will be staggered over regular interval of time. Like for example, if you order 1000 units and the delivery is going to happen like 250 units per week spread over 4 weeks. So that would be a case when assumption number 3 is not valid. If assumption number 3 is not valid, that's when we will be looking at production order quantity model. The fourth assumption is quantity discounts are not possible. We already discussed that. So if quantity discounts are available, then we will be looking at a different model for quantity discounts. Now, assumptions 5 and 6, they follow from some of the assumptions that you have made earlier. Only variable costs or setup costs and holding costs. And that comes from number 4. If quantity discounts are not available, then item cost is irrelevant. The only variable costs are the setup cost or ordering cost and holding cost. Now stockouts can be completely avoided, comes from assumptions 1 and 2. If the demand is constant and known, the lead time is constant and known, then we can precisely compute when to order and when to receive inventory in such a way that you never run out of stock. So assumption number 6 is derived from 1 and 2. Now let's look at how the inventory will go up and down under these assumptions. With time on the x-axis and on-hand inventory on the y-axis, and at one instant in time when an order is received, the on-hand inventory will jump up to the order quantity because the entire order quantity is delivered in one instant. Then, since demand is constant, the inventory will come down at a constant rate, at the demand rate. Then, at the time when the on-hand inventory reaches 0, the next order will come in because you can calculate exactly how many units are going to be demanded during the lead time, and when your on-hand reaches that point, then you will be placing the next order. So the next order will come right on time, and you will have a sawtooth type of inventory usage in this fashion. Okay. Now there's one more thing that we need to understand, and that is average inventory. So each order cycle begins with Q on hand and 0 ends with 0 on hand. So the average inventory is Q plus 0 over 2. So Q over 2 is the average inventory. And we'll be using this average inventory to compute the holding cost on an annual basis. If you take the average inventory and multiply by holding cost per unit per year, then we get the annual holding cost. Now, we want to develop a formula for order quantity that minimizes the total of these two costs, holding cost and ordering cost. So we want order quantities which will minimize the sum of these two costs. The holding cost is a linear cost going up like this, and the ordering cost, the annual ordering cost, okay, if you order in very small lots, then you will have lots of orders to place, so your annual ordering cost will be very high, and as the order quantity increases, the number of orders you have to place will decrease and your annual ordering cost will go down like this. Now you need to sum these two, and when you sum these two, the total cost will be a function like this. And the minimum here, the minimum point, will occur exactly where these two lines intersect, and we can prove this using calculus. So the minimum point of Q, that gives you the minimum total cost, and that is our economic order quantity. And also notice that around this economic order quantity, the curve, the total cost curve, is kind of flat. So even if our formula gives you kind of not very accurate answers, a little bit less or a little bit more, you will still be not very much off from the minimum total cost. And this property of economic order quantity is what is called robustness, and we'll talk more about robustness a little later. Now Q is your order quantity, D is your annual demand, S is your ordering cost per order, H is the holding cost or carrying cost, and these two terminologies are used interchangeably, holding cost or carrying cost per unit per year. Then your annual setup cost or annual ordering cost is how many orders we have to place times the cost to place one order. So if D is your total demand that must be ordered, and if you order at the rate of Q every time, then D over Q will give you the number of times you have to order, and this is the number of orders we have to place times S. This gives you the annual ordering cost. Next is annual holding cost, and that is the average inventory times holding cost per unit per year, so that will be Q over 2 times H. So that's your annual holding cost. When you sum these two, you get your total cost. Now in the previous slide we showed that when these two are equal, that's when you get the minimum total cost. So you set these two equal to each other and solve for Q, and you get your EOQ formula. So this is the EOQ formula. If you use this formula to find the order quantity, then you're guaranteed to have the smallest possible total annual cost sum of these two costs.